Muy buenas tardes a todos. Bueno, pues es un gran honor y un placer estar aquí con todos ustedes y recibir y introducir, es un honor para mí introducir al profesor Osheroff, que viene a dar una conferencia esta tarde aquí. Entonces quisiera empezar agradeciendo al profesor Osheroff su visita en Madrid y el haber aceptado participar en esta iniciativa. Y muy en especial quisiera agradecer a la Fundación del BBVA por colaborar con nosotros en esta iniciativa, por haber montado esta conferencia en este sitio tan especial y también por apoyar al instituto que dirijo desde hace ya un tiempo a través de la Escuela Nicolás Cabrera. Entonces, antes de dar la palabra al profesor Osheroff, que es a quien hemos venido a escuchar hoy todos, me gustaría decir muy brevemente que esta conferencia forma parte de una iniciativa que dedicamos a la memoria del profesor Nicolás Cabrera. 2013 es, de hecho, el centenario del nacimiento del profesor Cabrera y lo celebramos con un pequeño ciclo de conferencias entre las que se encuentra la de esta tarde. Me consta que ya antes de que yo llegara al Instituto Nicolás Cabrera, varios premios Nobel visitaron nuestro instituto. Está Bednorz, que descubrió la superconductividad de alta temperatura crítica; Rohrer inventó el STM; Sturmer y Laughlin descubrieron el efecto Hall cuántico fraccionario; y Tony Leggett, que visita también frecuentemente la Universidad Complutense. Tony Leggett recibió el Premio Nobel por la teoría del helio 3 superfluido. Es un honor y un placer tener ahora al físico experimental que hizo el descubrimiento correspondiente. Osheroff inició sus estudios en 1967 en Caltech y siguió las famosas clases de Richard Feynman, tituladas Feynman Lectures on Physics. Osheroff es sobre todo un físico de bajas temperaturas experimental. Él mismo construyó el instrumento con el que consiguió hacer los experimentos que le llevaron al Premio Nobel en 1996. Estos experimentos los hizo durante su tesis doctoral en 1972. Y en estos trabajos lo que hizo fue descubrir las fases superfluidas del helio 3. El helio 3 líquido es un material muy curioso, es el sistema más puro que uno se puede imaginar. Y el descubrimiento de la superfluidez en él representó un cambio conceptual de la física en su momento. Osheroff hemos podido ver esta semana que disfruta en el laboratorio, disfruta hablando con los estudiantes y es un apasionado de la técnica y de la instrumentación. Es un fotógrafo compulsivo y participó en la comisión que investigó el accidente del Columbia. Osheroff ha tenido muchos reconocimientos, como obviamente el Premio Nobel, y a mí me gustaría añadir que en su universidad también ha sido reconocido como un excelente profesor. Ahora Osheroff dará una conferencia para ustedes sobre su visión de cómo se hacen los avances en la ciencia y creo que todos hemos venido a escucharle. Thank you very much, Doug. All these people came to hear you and I guess it's your turn now. Thank you very much.
Go to the lecture now.
Yes.
Well, I'm very honored to be here today. I hope this lecture will, in fact, illuminate perhaps some of the processes by which science is done. I would like to thank the Foundation for hosting these events. I dare say that they've actually hosted other events that I've been a speaker at in Mexico City or just outside Mexico City. So it is certainly a very great honor, and I'm very pleased to be able to be here today to give this lecture. See if this works out now. It's up there, good. So I should tell you that I'm a very avid photographer, and what you're looking at in the background are some of my photographic images. This is the Golden Gate Bridge with San Francisco in the background. So to start the talk, those discoveries that most change the way we think about nature cannot be anticipated. How then are such discoveries made, and are there research strategies that can increase one's chances of making such a discovery? And that is really what this talk is all about. The background is the Grand Canyon at sunset. Let me illustrate this with a linked chain of discoveries and inventions involving some very prominent scientists of bygone age. This is one of my great heroes because this is Heikki Camerlionis, who first liquefied helium, and then he actually did with helium exactly what Dewar, let me explain a little bit. Camerlionis and Dewar were in a competition to see who could first liquefy the lightest and most inert of the atmospheric gases, and it looked like Dewar had won when he succeeded in liquefying hydrogen, which is a liquid at 23 Kelvin, 23 degrees above absolute zero. And then so Camerlionis eventually was able to acquire a large enough sample of helium, which was very rare at that time, which he succeeded in liquefying. And then he did exactly what Dewar had done with hydrogen. Dewar had pumped on the vapor above the liquid, causing more liquid to evaporate, and ultimately this sample, the hydrogen, froze. So he not only determined the temperature where hydrogen was a liquid, but also where it became a solid. So Camerlionis then tried to do the same thing with his liquid helium. He was able to show that at atmospheric pressure, its temperature was roughly 4 Kelvin. And then he pumped on the vapor above the liquid in order to see where helium solidified. And I think he spent over a year fruitlessly trying to solidify helium by cooling it. Now, I personally have cooled liquid helium to a temperature of 1/10,000th of a degree above absolute zero, and it stays very happily in a fluid state. And this has to do with quantum mechanics, which were just being developed when all of this work was done. So Camerlionis eventually gave up on his efforts to solidify helium, and then he looked around for some interesting question of the day that he could answer with this quite remarkable set of refrigeration devices that he had developed. People were arguing about what would happen to the electrical conductivity of a very pure metal if one could cool it to absolute zero. There was one school of thought that said that if it was a very pure metal and you cool it down, you eliminate the lattice vibrations due to heat, which scatter the conduction electrons. So as you cool it, the electrical resistivity would drop towards zero. The other school of thought suggested that at some temperature, the conduction electrons, which were free to roam around the interior of the metal, would recondense on the ions from which they had come, and all electrical conductivity would cease. So Camerlionis got a very pure sample of mercury and gave it to his colleague Gilles Holst, and asked Holst to measure the electrical resistance as a function of temperature as he cooled it down. And these data points up here show some of his data. As he cooled it, in fact, the electrical resistance did drop. But then at a temperature a little above 4.2 Kelvin, there was a discontinuous drop in the electrical resistance of the mercury to a value that was less than 10 to the minus 5 ohms, which is the resolution of their equipment. This was, in fact, the first observation, the first time superconductivity in a metal had been created. It actually wasn't understood well at the time, and not very shortly after this, just a few years after this, Camerlionis was awarded the Nobel Prize. It wasn't clear that it had anything to do with superconductivity, but rather his liquefaction of helium. So let's look at the relevant research strategies that allowed this discovery, that is, superconductivity, to be made. First, use the best instrumentation available, and in this case, all these refrigeration processes had been developed by Camerlionis himself. Second, don't reinvent, borrow technologies you can. Now, Dewar and Camerlionis were rather bitter rivals in this business of refrigeration and cooling these various liquids, gases into liquid and finally into solid state. But in fact, when Dewar invented the Dewar flask, Camerlionis was very happy to use that technology in his own experiments. So don't reinvent, borrow the technology you can, and then look into an unexplored region of the physical landscape. In this case, no one had actually studied the properties of solids, let alone conductors, at very low temperatures. And so, in fact, it is in this case where there was whatever was to be discovered had not been discovered yet. And fourthly, failure might be an invitation to try something new. So after failing to solidify liquid helium by pumping on the vapor, Camerlionis turned around and decided to see what would happen to a metal if one cooled it to very low temperatures. So indeed, and I dare say that this failure might be an invitation to try something new is very good advice, I think, for all scientists. And finally, beware of subtle, unexplained behavior. Don't dismiss it. So Camerlionis noted in his lab book that at a temperature of about 2 Kelvin, the liquid helium that he was pumping on the vapor above the liquid helium, and the helium was boiling. At about 2 Kelvin, the boiling ceased very abruptly. So he noted this, but in fact he didn't follow up. If he had, in fact, he would have discovered superfluidity in helium-4, which was done by someone else later on. So it was probably this person here, this is Peter Kapitsa, a Russian physicist, who first recognized the remarkable nature of liquid helium below a temperature of 2.17 Kelvin. He measured in I dare say, it goes without saying that it was the bleak winter of 1937. Kapitsa studied the viscosity of liquid helium-4 and found that at 2.17 Kelvin, the viscosity essentially vanished. It had become a superfluid. Kapitsa shared the Nobel Prize for Physics in 1978, 41 years after his groundbreaking experiments. I don't understand why it took so long. As someone who uses superfluid helium, I find it a very important discovery that he made. But in fact, it was 41 years before he was able to get his Nobel Prize for his work, which he shared with two very unlikely colleagues whose work had absolutely nothing to do with his own work. And those gentlemen were Arno Penzias. When I was at Bell Laboratories, Arno Penzias was my boss's boss's boss. So you can see where I was in the chain of command at Bell Laboratories. Anyway, Arno Penzias and Robert Wilson were interested in looking at the radiation coming from outer space. It had already been discovered, but the nature of that radiation had not been. AT&T had been doing some early experiments on satellite-based telecommunications using this spectacular piece of equipment. This is a horn antenna which does not couple to radiation coming from terrestrial sources. But inside this shed was in fact the world's most sensitive microwave receiver. And that receiver relied on as a key element on the maser amplifier. Now the maser itself had been invented by Charles Townes, who I think is now 97 years old and still quite active. There's a set of meetings that are held every year at UC Berkeley, and Charles Townes comes to all of those things. Anyway, so this is Charles Townes and Jim Gordon, who was his associate, and together they built the first ammonia maser. This technology, however, would not help Penzias and Wilson, but after this first step had been made, other people realized that there were ways that one could implement this kind of technology into a much cleaner package. In particular, Nicholas Bloomberg had realized that if you took a ruby rod and suitably doped it, in fact, you could use that as a maser amplifier. So eventually, Penzias and Wilson were testing their instruments, so they looked at the radiation coming from a place in the sky which was known to have no bright radio sources, that is radiation coming from the sky in the, well, probably maybe the microwave part of the spectrum. Anyway, so the data back in those days was all obtained on strip chart recorders. So the paper would run underneath the pen that moved back and forth according to the voltage that was applied. And so they're sitting here, this is, they're looking at the noise coming in from the antenna, and then they have a microwave switch that allows them then to compare that signal with the radiation being radiated by a black body at a temperature of 4.2 Kelvin. So they do a bunch of calibrations then, and their conclusion was there was excess radiation coming in that wasn't understood at the level of about 3 Kelvin. That, of course, is the cosmic microwave background radiation that we all know about today. But Penzias and Wilson didn't trust their measurements, and particularly they didn't trust the equipment that they had borrowed from AT&T. So they climbed up inside the antenna, and what they found was that the pigeons were roosting inside the antenna. So they knocked down the pigeon nests and mopped up the pigeon droppings, and I think there were a few corroded copper plates that had to be replaced. But virtually nothing that they did could get them to eliminate this excess noise that they didn't understand. Of course, ultimately, this noise was understood. But let's look at the relevant research strategies that allowed them to make this discovery. First, and again, use the best technology available, and luckily for them, it was given to them, or loaned to them anyway. Secondly, don't reinvent the wheel, borrow if possible. These look like the same strategies that I just described before. Thirdly, look into a region of parameter space that's unexplored. People knew that there was microwave radiation coming from outer space, but in fact, no one looked at it in the sort of detail that Penzias and Wilson did. And finally, and this is perhaps in their case most importantly, understand what your instrumentation is measuring. It would have been so easy for Penzias and Wilson to simply say there is excess noise in my preamplifier and subtract that from all of the readings, but they didn't. They actually pursued this. But this was just the start of a rather long story. After Penzias and Wilson's work, other researchers started looking at this fossil radiation, which people already believed was left over from the epoch in the expansion of the universe when protons and electrons combined to form neutral hydrogen. So that was about, I think, 400,000 years after the Big Bang. Of course, now it's several billion years after the Big Bang. So this is John Mather and George Smoot were working at Lawrence Berkeley National Laboratory, and they developed. George Smoot was at Lawrence Berkeley National Laboratory, and John Mather was actually on the East Coast. Anyway, they were able to create a satellite that went into orbit and would measure the intensity of this radiation as a function of wavelength. And what they found was this spectrum. This is the intensity as a function of wavelength. And this red curve is essentially a perfect black body curve, which suggested that this radiation was characteristic of the temperature of the universe at the point where electrons and protons combine to form neutral hydrogen. At that point, the radiation decoupled from the matter in the universe. And you might ask why, in fact, if the radiation did that, why was the radiation temperature so low? Well, what happens as the universe expands, the radiation scatters off of the protons and the electrons, and as it does that, it cools. And so this, in fact, really told us for the first time something about the universe very shortly after it was formed. So after the COBE satellite work, there's been more really spectacular work done. This was the Cosmic Microwave Background Explorer, which is a much more aggressive satellite. And if you just look at the radiation without much resolution, what you see is that radiation is at a higher temperature if you look in the direction that the satellite is going, and if you look in the other direction, that's where the direction that the satellite was from, in fact, it's colder. This just has to do with Doppler shifts. So this has nothing to do with the distribution of the incident radiation. So it's very easy to get rid of this, and then what you find is this band here is the band of the plane of the Milky Way galaxy. So this is a lot of microwave radiation generated there, and you can subtract that. And then what you're left with is this kind of uniform blotchiness. And now we understand that this blotchiness is due to fluctuations in the density of the universe just 400,000 years after the Big Bang. So this is quite remarkable that we can look back in time at something that happened long distances from the Earth. So this is the latest, this is that I know of anyway, satellite. This is called WMAP, and it shows the fluctuations in the temperature of this radiation with very high resolution. The W was for Wilkinson, David Wilkinson, who was a pusher for this project, but died before the satellite actually got up into orbit. This is one of the problems dealing with NASA and satellite in general, is that it's possible that by the time the satellite makes it up into orbit, you're no longer there to look at the data. Okay, so now I'm going to shift gears. By the way, this is a little piece of the Iguazu Falls. It had been raining violently for a week before my wife and I actually visited the falls. This is a black vulture. Anyway, the process of advancing science often leads to inventions and technologies that directly benefit mankind. I think everyone would agree with that. But it is not possible to know from where an advance might come that could solve a particular problem facing mankind. Consider, for example, one of my favorite pieces of technology, that's nuclear magnetic resonance. Okay, nuclear magnetic resonance was actually first invented by these two gentlemen, Felix Bloch at Stanford University and Ed Purcell at Harvard University, or as we people at Stanford like to say, at the Stanford University of the East. We're kind of competitive that way. Anyway, so Felix Bloch was I would say, not a very kind person, a very nuts and bolts, very down to earth, and I would say he did not couch his phrases. So when these two gentlemen got the Nobel Prize 6 years after their discovery, the press, of course, interviewed them and want to understand the nature of nuclear magnetic resonance. And after a while, of course, these people really want the inventors to explain how nuclear magnetic resonance works. Press have a lot of trouble understanding that. So they then, and this happened to me too, they then ask a simpler question: what do you think nuclear magnetic resonance might be good for? And of course, Felix Bloch interpreted that kind of as an insult. He didn't think it had to be good for anything, so his answer to that question was damn little. Okay, and then Ed Purcell was asked the same question after failing to explain how NMR worked to the press, and his answer was, well, perhaps one can use nuclear magnetic resonance to calibrate magnetic fields. So this is what the inventors of NMR felt that NMR might be good for. And now we're going on a journey to find out what NMR has actually been good for, because these gentlemen had no clue. So eventually people were able to create very homogeneous magnetic fields, and if they did NMR looking at resonances in the hydrogen atoms, basically proton resonance, they found that in organic solvents, not all of the protons, hydrogen atoms, resonate at the same frequencies. There are shifts of a few parts per million, and depending upon what organic solvent they have, they can get triplets and quadruplets that were very closely spaced. So this basically really told us that NMR was a real useful tool for organic chemists. And I think today, if you go into any organic chemistry laboratory, you'll find that they still have nuclear magnetic resonance spectrometers. The next big development was made by Richard Ernst. Now, I've known these guys. There used to be a set of NMR Gordon conferences, which I would attend because I do NMR. And so Richard Ernst actually invented a much better way of doing nuclear magnetic resonance. Originally, what happened is they would have a tank circuit, that is to say, a coil of wire with a capacitor in it at a resonant frequency, and they would sweep a magnetic field. And when they got to the magnetic field where the precession frequency of the nuclear spins was the same as their applied resonant frequency, then in fact there would be an absorption peak, but actually it's a dip. And this was a very slow process. So what Richard Ernst realized was if you applied a very powerful rotating magnetic field in the plane that's rotating at the same frequency as the spins, in less than a microsecond you can tip all the spins and they would all precess, and then these precessing spins induce a voltage in a pickup coil. You take the Fourier transform of that and it tells you the frequency of all the spins that are precessing. A remarkable advance in nuclear magnetic resonance. Now, and that allowed one to actually measure molecular bond lengths in even complicated organic molecules. But Richard Ernst had a colleague who was working with him, and that was Kurt Wutrecht. And here's Richard Ernst in 1991. He was awarded the Nobel Prize for his work in NMR, not in physics, but this time in chemistry. But his colleague, who worked with him during most of this time, did not share the Nobel Prize. And so the colleague's name was Kurt Wutrecht, and I would meet him at these NMR conferences. And I said, Kurt, how did you feel when Richard Ernst got the Nobel Prize and you didn't share it? You must have been disappointed. He said, no, I wasn't disappointed. I was mad. So Kurt Wutrecht then proceeded to develop a complicated set of pulse sequences which allowed him to not just determine molecular bond lengths, but the entire three-dimensional configuration of complicated organic molecules. Quite a remarkable achievement. And so here, so this was 1991, 11 years later. Kurt Wutrecht gets his own Nobel Prize. And again, it's in chemistry, and if you look very carefully, you'll notice that he's smiling. In fact, I've never not done a detailed study of this, but I think the moment that the King of Sweden gives you your Nobel diploma, it's hard not to smile at that point. So I was actually involved in NMR through most of my research career, and I had a mixture. This is what's called a Pomeranchuk cell. I won't explain it. It's liquid helium-3 under very high pressure. Part of the liquid is converted to solid, and in the process, the system cools. For every % of the liquid you convert to solid, the temperature drops by 1/1000th of a degree. Now, you say that's not a very efficient thermometer, but if you start at 10 milledegrees, you can then cool 90% of your sample to essentially a temperature of 1 millidegree. And so that's what was going on in here. This is basically the bellows I pushed in to compress the helium-3, which I show here in gold because helium-3 is actually quite expensive. And so then I applied a magnetic field which was larger at the bottom of my sample than it was at the top. And if I swept the NMR frequency, then there would be a resonant layer which would move up and down depending upon which direction I swept it. So this allowed me to actually plot out the liquid and solid NMR signals separately, find out what their frequencies were. There seems to be a slide missing. This happens a lot to me. But the bottom line was one could use this to separate out the liquid NMR signal from the solid NMR signal. And I'll tell you more about that later, but in fact it turned out that the liquid had actually become a superfluid. And that's what I got the Nobel Prize for. But this same technology can be used using pulsed NMR. I wasn't using pulsed NMR, where you apply magnetic field gradients sequentially in 3 different directions. And when you do that, in fact, you can actually do something that's a little bit like X-rays, but NMR has many advantages over X-rays. This is a very healthy human knee. I know the difference. My right knee is made of titanium now, so one doesn't do NMR on that anymore. But in fact, one can see very minute details in the anatomy of the knee using MRI, as it's called. And so for their developments in NMR, this is 2003, just 1 year after Kurt Wuttrich was awarded the Nobel Prize in Chemistry. Paul Lauterbur and Peter Mansfield shared the Nobel Prize, not in physics, not in chemistry, but in physiology or medicine. So it's quite a remarkable string of advances for a single technology. It is conceivable, but I'm giving up hope, that there will be one more Nobel Prize given for NMR, and that is for something which is called functional magnetic resonance imaging. So what you do then is put on pulse sequence with sequences which are sensitive to the rate that the nuclear spins return to being along parallel to this applied magnetic field. And what happens is then you can see those regions in the brain that are processing information, those spins recover much faster. And so you can actually see those places that are thinking, but of course you don't know what the patient is thinking about. Maybe he's saying, my God, this is an expensive procedure. Anyway, so that's just one technology I've gone through and its development over time. And it's quite remarkable that you can get something so useful to mankind out of something that looked like it was a toy to begin with. So now I'm going to talk about my own discovery, and I first will introduce to you my family, that is to say the family that I'm from. My father was a medical doctor, and I give him most of the credit for my interest in science. He would bring things home that his patients had given him for me to play with. And some of these things I managed to make into nearly lethal devices. I wired a bunch of capacitors together and charged them up to 600 volts. The idea was then to discharge that over the primary of a transformer. I was ultimately able to get sparks that were something like 20 centimeters long. Probably 100,000 volts or more. But before I killed myself, I managed to discharge the 600 volts across my body. And a very violent contraction of my muscles propelled me across the room. And when I woke up, I sort of kind of knew how I'd gotten there, but I had no recollection of this violent process that had occurred. Anyway, so I think I didn't tell my parents about that. But I did a lot of other things. My older brother actually went into medicine, but anyway, there's a family of 5 children. So when I was so I would say my father was probably the person that was responsible for my interest in science. He gave me lots of science things to play with. I think in terms of actually understanding science, probably not my physics teacher, but my chemistry teacher. This is my high school chemistry teacher, William Hawkes was his name, and this is me right here. And one day William Hoppe came into the classroom and he had a milk carton. There was something inside it. He shook it. He said, research, scientific research is like trying to find out what's inside the milk carton. He said, every time you do an experiment, you're asking a question of nature. Nature has to answer your questions, but nature's answers aren't what's inside the milk carton, but rather something about what's inside the milk carton. So then you have to ask nature more questions by doing more experiments. And to this day, that is the way I think about scientific research. Well, I would say nature is a woman. Of course, we all know that. And if you ask women questions, frequently you don't understand the answers, particularly certain kinds of questions. And so the trick is to ask questions that will force nature to give up one of her secrets. And that's the way I like to think about research. This is, I guess, the other person that really influenced me greatly, and this is Richard Feynman. I think everyone recognizes a picture of Feynman. Feynman had invented already by the time I got to Caltech as an undergraduate his famous Feynman lectures on physics class. And I dare say for people like myself, this was heaven on earth to learn from Richard Feynman. But there a large number of my classmates felt that learning from Feynman was cruel and unusual punishment. So my freshman class had started out at 192, and only 120 returned for their sophomore year. And I think Richard Feynman was responsible for much of that attrition. However, for the 120 that stayed, almost all of us wanted to become physicists, and certainly I did. So when I was at Caltech, I eventually got involved in a research project. It is infrared astrophysics, and I can't show infrared because you can't see infrared, but basically it's a matter of scanning the cosmos, looking for bright infrared sources. And so I found this very exciting, but after a while I started thinking about what I'd always wanted to do, what I always did when I was a child. I loved doing experiments. And the trouble with astrophysics is you can't do experiments. You can't change the temperature of a star and see what happens. And so in my senior year at Caltech, I'd already applied to schools for graduate study, and I applied mainly to schools with good astrophysics programs, but then I realized that this is probably not the field for me because it really doesn't allow me to do experiments. So Mossbauer would come to Caltech every spring, and I asked Mossbauer where he thought I should go to school if I wanted to do condensed matter physics. And Mossbauer looked at this list of 8 schools, and I got into every school I'd applied to. But Mossbauer said, well, you know, you've applied to 8 schools, but none of them are good in condensed matter physics. That wasn't reassuring, and so I asked him where he thought I should go of the list of places that I'd actually applied and been accepted to. And he suggested I should either go to Cornell University or the University of Washington. And since I'm from Washington State, I didn't want to go home. And so that's how I ended up at Cornell University. Far above Cayuga's waters, with its waves of... This is my alma mater, and that was the alma mater. But anyway, this is Cornell. You can't see it very well, and Lake Cayuga's down there somewhere. But this was kind of an interesting place. I must say that almost the first day that I showed up at Cornell University, I met someone who was literally going to change my life. This little girl here, this is Liu Xiaodai, who is been my wife now for 40-some years. But we met. She was there to be a graduate student and in biochemistry, and I was there to be a graduate student in physics. And so we dated a bit, and then the term started, and I would call her up and say, how about a movie? She said, too busy, hang up. But I was persistent, and eventually, well, actually nothing happened until that summer, and it was after she had completed all her coursework. She had started doing research. She had to come to the physics department to get liquid nitrogen. So I then invited her to the most romantic event of the season, the physics department picnic. And that was it. Okay, so anyway, I would say Cornell did a lot of things for me, including giving me a wife. So when I got to Cornell, there were two lectures that were given in the physics department the first semester on new refrigeration technologies that I felt would give me the opportunity of looking at nature in a new and different realm. The first of these is called the helium-3, helium-4 dilution refrigerator. And I don't know that I want to explain how it worked for this audience, but it's fairly simple. You have essentially pure helium-3 at the top, and then a mixture of helium-3 and helium-4. The helium-4 is superfluid below that. And then if you pump on here, mainly the helium-3 comes off, not the helium-4. So then more helium-3 diffuses across the phase boundary into this helium-3, helium-4 mixture. And in the process of doing that, it cools. So this I actually built one of these things, and it reached a temperature of about 15 thousandths of a degree above absolute zero. Not bad for a first-year graduate student, I think. So this is that device. This is the mixing chamber where the cooling occurred. But this, in fact, wasn't as I wanted to get much colder than 15 thousandths of a degree. And there was a Russian theorist named Isaac Pomeranchuk that when helium-3 first became available, Pomeranchuk started thinking about what its properties would be. Now, I should tell you that Pomeranchuk was mainly professionally interested in high-temperature plasmas. It's kind of remarkable how broad theorists can be. So this is the entropy, or the degree of disorder in this is liquid helium-3, and it's disordered. This is solid helium-3, and it's disordered because the nuclear spins can point either up or down until you get down to a temperature on the order of 1,000th of a degree, and then that entropy drops. The liquid entropy is linear in temperature. And so if you start with liquid at some temperature and you solidify it, you form solid at a very, very low temperature. And so this was a refrigeration device. What actually happens in real space, this is the melting pressure. So the solid in this region and liquid below that. And so if you compress up to the melting curve, as you convert liquid to solid, you go along the melting curve to lower and lower temperatures. And this was a way of getting to temperatures of order 1,000th of a degree above absolute zero. So this is the Pomeranchuk cell that I built. It didn't have all those wonderful colors in it, of course. That's added so you can understand what's going on. So this gold is the liquid helium-3. It's rather expensive. Helium-3 doesn't exist in nature. It results from the decay of tritium. And so in 1948, when the United States and the Soviet Union were competing to build a hydrogen bomb, there was a guy at Los Alamos named Ed Hamel. And Ed Hamel's job was to keep the nation's tritium supply clean, which meant filtering out the helium-3. And then he didn't throw away the helium-3 or release it into the atmosphere. He saved it. And without getting any permission from the Department of Energy, he decided to liquefy the helium-3 and measure the vapor pressure as a function of temperature. And without getting permission to do so, he then published his results. And not only did he say what he'd seen and how the vapor pressure varied, but in fact, he said how large his sample was, which told the Russians something about how much tritium the United States had in their efforts to build a hydrogen bomb and how long they'd had it. So I'd interviewed him. He was, I think, close to 100 years old. I was a telephone interview for a talk I gave for the American Physical Society. Anyway, so that's where helium-3 came from, and that's why it's expensive, and it's getting more and more expensive today. So the idea was to compress this and solidify it, and I did that using a hydraulic press. Basically, these are bellows, beryllium copper bellows, And then I measured the melting pressure with a capacitive pressure transducer down here, and I measured the temperature using nuclear magnetic resonance on platinum wires. The NMR signal is proportional to 1 over the temperature. So before this thing, I did anything with it, I dare say that the summer after my third year of graduate study, Phyllis, Lou, and I were married. And so that's a long time ago. And Phyllis, stand up so that the people can understand. So that's my wife. And I go around the world with her a lot, giving talks. This is my favorite picture taken on our honeymoon. So I don't know how many young people are in the audience. Of course, everyone takes cameras now, but get a picture of your bride on your honeymoon. Anyway, this is my favorite picture. This is actually at something called Inspiration Point in Grand Teton National Park. It's a wonderful place in Wyoming. Anyway, so then, of course, I still had to do my PhD thesis, and I had no idea. It wasn't going to be building a piece of apparatus. I had to do some science. So Dave Lee got a plot. People were looking at the shift in the melting temperature of helium-3 as a function of magnetic field and temperature. And so the theory suggested, in fact, the shift in the melting temperature would be a very small shift. But then someone at another university actually made measurements and found a huge shift. And so this looked very exciting, and Dave Lee suggested I go in there and confirm these results. That's the first thing you want to do. Well, my measurements are these red triangles. So they're entirely consistent with this simple theoretical curve, but there's a lot of scatter in the data. So I kept trying to get better temperature resolution with my nuclear magnetic resonance, and eventually 2 other students who were waiting to use the same NMR magnet. These were iron core electromagnets. This thing probably weighed 3,000–4,000 pounds, and so they went to Dave Lee and argued that I'd been monopolizing this key piece of equipment and that I should have to give it to them. And so, in fact, I did that, and it was only then that I started doing the experiment that won me the Nobel Prize. So I didn't have a thermometer, but I'd measured the melting pressure as a function of temperature, and so I realized I could use that as a thermometer. So this is data, November 24th, 1971, and I'm compressing, and so I'm forming solid, and as I do, the system cools, melting pressure increases. Here, this is, I use a capacitance pressure transducer. I have to rebalance the capacitance bridge, and it continues to cool. And then at this point, which I later labeled as A, there was a rather sharp decrease in the rate of cooling. And so I thought, surely something had gone wrong. And so I stopped doing this experiment, and I'd started this run at an initial temperature of 22 thousandths of a degree. I didn't really know the temperature I'd gone down to, but it was quite a bit colder than that. This was actually the day before Thanksgiving, 1971. And so I said, well, okay, I will melt the solid and then pre-cool over this long Thanksgiving holiday, essentially a 4-day holiday. So Thursday, Friday, Saturday, and Sunday, I pre-cooled. And so I tried this experiment again the next Monday. Oh, darn it. I don't know why. I don't seem to have the right set of, well, let me just tell you what happened. So the next time I do this experiment, in fact, I find exactly, starting at 15 milledegrees, I see exactly the same kink at exactly the same pressure. I said, there's no way that can be a coincidence. This has to be the signature of some highly reproducible phase transition inside this mixture of liquid and solid helium-3. Now, I can tell you the time that this was done when I realized this was 2:30 in the morning, and I'm afraid you will get there. Okay, so we have to go back now. So this is what I'd seen, And ultimately, I found that you could see there were two transitions. This A transition, I said we could have given these things much more imaginative names. This was A, and the lower temperature transition was called B. And then you could see these both on cooling and on warming. And so they were definitely real transitions. I actually invented an early form of magnetic resonance imaging where I applied a magnetic field gradient, so it was larger at the bottom than the top. And then I swept the magnetic field. Actually, I got this idea after talking to a very bright theoretical chemist, Michael Fisher. I don't know how many of you know Michael Fisher, but a very brilliant chemist. So he was the one that really told me how solid helium-3 would grow inside this cell. And so, but then eventually the other graduate students wanted to use this iron core electromagnet, and so I had to give up the magnet. And before I did that, though, I took these data, which basically what I'm doing is sweeping the NMR frequency slowly up and down, and then this is a strip chart recorder. Time is increasing in this direction to the left, and pressure is increasing downward. This shows what the pressure is doing. It's increasing. There was this funny blip here in the pressure. But in fact, I looked at these signals. Most of this is solid helium-3, but there was a little liquid signal between the solid peaks. And I looked at this, and at this little drop in pressure, which we called the B transition, the liquid NMR signal dropped by a factor of 2. And I remember exactly how I felt when this happened. I think the hair stood up on the back of my neck, and I realized that I had really come on to something. So I wrote in my lab book at 2:40 in the morning, have discovered the BCS transition in liquid helium-3 tonight, and then I explained why. And so then this was my moment. I ran around the basement of the physics building to share this exciting news with some of my fellow graduate students, but there was no one there. In desperation, I went up to the 6th floor where the theory students hang out, hoping that one had fallen asleep at his desk. But it turned out I was the only person in the physics building that night. And so at 4 in the morning, I couldn't stand it anymore. I called up my thesis advisor. Now, I always tell my graduate students that they should feel free to call me up, but it better be good news. So Dave Lee called me back at 6 a.m. He wanted more details, but that was really the most exciting moment of my life, I think, to have recognized what it was that I discovered. So then I think there were actually 2 professors I was working with. David Lee was my thesis advisor, and Bob Richardson, who was really much more of an expert at nuclear magnetic resonance. And so Bob Richardson suggested that we should look at the NMR signal as we go through these transitions. And what we found was that this is mostly solid helium-3 NMR signal. The liquid signal is this little tiny thing. And as we cooled below the temperature of what we called the A transition, the liquid NMR signal moved out from underneath the solid NMR, and it moved to higher and higher and higher frequencies until we got this little drop, which this is the B transition. And exactly at that moment, this signal disappeared. So obviously all of these things were correlated together, and I plotted up the liquid NMR frequency squared minus the solid NMR frequency squared, and found that it was independent of the strength of the applied magnetic field. So I didn't understand this at all, but I sent a copy of a preprint to Tony Leggett. And Tony Leggett, I think within about 2 months, produced a paper that explained virtually everything that I had observed. So let's look at the strategies that really allowed me to do this. First, again, utilize new technologies to view nature from a new perspective or a different realm. Secondly, and this is a good one, I think, don't give up when things are going badly. Failure may be an invitation to try something new. And I think that's really relevant to this business that I had to give up the NMR magnet, so I couldn't do NMR anymore. But in fact, I realized that I could use the melting pressure as a thermometer. Spend a little bit of time doing something different. Curiosity-driven research can be fun and be rewarding. And so I think everyone needs to now and then think about Gedanken experiments. What if I did this? Can I guess what in fact I'll see? And if you can't guess it, then do the experiment. Avoid too many commitments. Now, I'd married this Chinese girl, and Cornell University was offering a course in conversational Chinese. And so I was very excited about taking this course. But then I thought, you know, this is my last year of graduate study. I think I'd better not do that. And I dare say that I, to this day, only know a little bit of Chinese, mainly insults that my wife taught me, such as 笑死我了, which means I laugh myself to death. 你做梦, you're dreaming anyway. So that's the extent of my Chinese. But in fact, I did get a Nobel Prize after all, so I wasn't a complete failure. Back off from what you're doing occasionally to gain a better perspective on the task at hand. And I think this is really true. We become myopic when we focus too tightly on our work. So this is Dave Lee and Bob Richardson and me, and we're showing off our new Nobel medals. And as I've said to another audience already, the gold medal is not solid gold. I decided I would look into what it was, and so I Googled it, I think, and it turns out the Nobel medal, I believe it's 20% silver, 80% gold. Anyway, so as a result of that, however, the Nobel medal resides in the safe deposit box in the bank, and it does no one any good there. But in fact, they give you facsimiles that look just like the real thing, except they're not quite as heavy. So Tony Leggett, who is the one that really explained all the spin dynamics of superfluid helium-3, in fact, I just touched on some of the remarkable behavior that he had predicted before we saw it. So here he is in 2003 accepting his own Nobel Prize. He shared the Nobel Prize. In physics, for some reason, the Nobel Prize almost invariably gets shared amongst 2 or 3 people. So he shared the Nobel Prize with 2 Russian theorists for their work on superconductivity. Superfluid helium-3 is more closely connected to superconductivity than it is to superfluidity in helium-4. And finally, now we're almost done, I show my beautiful Pomeranchuk cell again, and I put up the names of a bunch of people who made contributions without any one of which I probably would not have made the discovery that I did. So John Bardeen and Cooper and Schrieffer developed the theory that explains superconductivity in metals. That theory was then applied by a number of people to predict that there would be superfluidity in helium-3, but a lot of people looked for it and no one had found it. Let's see, Schrieffer. Phil Anderson was the one that ported the BCS theory and applied it to helium-3 atoms, which are Fermi particles, just like conduction electrons in metals. And so Anderson, of course, Pomeranchuk for his wonderful proposal for a new refrigeration technology. Without that, I suppose I would not have discovered superfluid in helium-3. Ed Hamel was the person that single-handedly decided to save the helium-3 that was resulting from the decay of tritium, and he is really the father of helium-3 physics. John Wheatley was an experimental physicist that developed a lot of the technologies that were used in these studies. Lev Landau was a brilliant Russian theorist. And over here, Edwards and Hall invented the helium-3, helium-4 dilution refrigerator, which was necessary in order to get the helium-3 cold enough to actually do Pomeranchuk cooling. So Edwards and Hall invented the dilution refrigerator. Bloch and Purcell, of course, invented NMR, which was directly responsible, allowed me to understand what it was that I discovered. So let me leave you with the following message, that advances in science are seldom made by individuals alone. They result from the progress of the scientific community at large, asking questions, developing new technologies to answer those questions, and sharing their results and their ideas with others. To have rapid progress, one must support scientific. Now, I put this in here because I was giving this talk to the American Physical Society. To have rapid progress, one must support scientific research broadly and encourage scientists to interact with one another and to spend a bit of their time satisfying their own curiosities. This is how advances in science are made. And let me leave you with a message, not too many graduate students in the audience, I suppose, but to decline a challenge for fear of failure is to fail at the onset. And thank you for your understanding. I should tell, well, we don't see it, but the bird is a great egret, and I took that picture at the Palo Alto wetlands. So if you ever come to Palo Alto, ring me, tell me you're coming, and I'll take you to the Palo Alto wetlands early in the morning, and we'll see some wonderful birds. I think I'm supposed to come over here.
It's okay. So
I should stay over there?
Please, I think yes. Yes,
okay.
That's okay. Yeah. Thank you very much. So thanks for such a beautiful talk. So, ahora pasamos al turno de preguntas. Quiero recordar que las preguntas, por favor, el planteamiento debe ser breve. Muchas gracias. Sí, por aquí.
You say in one of your points to study new fields, okay?
Yeah.
Are they still new fields to study? And secondly, or is it just a sort of race of investors putting their money in a group of different groups of scientists that want to win the race to discover something new? Thank you very much.
Okay. Well, I mean, I think there are certainly things that we're discovering all the time. I mean, the high-temperature superconductors, it wasn't that long ago. I mean, there's all sorts of graphene and all of these different things. I mean, there is a steady, I think, stream of new observations of new behavior that we don't understand. And so I think that I do not feel that I will be out of a job for quite a long time. At least that is my profound hope, but also my strong belief as well. Thank you for your question.
Muy bien. ¿Más preguntas?
El otro día atendí también a la conferencia que dio en la Universidad Autónoma y dijo que los cuadernos de laboratorio se los habían quitado, que ya nunca más los pudo tener, se los llevó la Fundación Nobel. Mi pregunta es, ¿todavía conserva su celda Pomeranchuk?
Sadly, it was on display at Cornell University for quite some time, and it disappeared. So someone must I hope that whoever stole it is enjoying having it, but probably I would have enjoyed having it even more.
Muy bien, ¿alguna pregunta más?
Buenas, nos conocimos el otro día muy brevemente. Le quería decir que a lo mejor usted, como ha valorado pues, la gran importancia que tienen los avances científicos, a lo mejor, dada su posición, podría enviar algún pequeño mensaje, un poco de lobby al gobierno de aquí, a ver si invierte un poco más, si cuida un poco más la investigación aquí en este país. Simplemente ese comentario, que a lo mejor, como están las cámaras, pues quiere un poco más de notoriedad.
Yeah, well, I mean, I think it's worth noting that if I went back through my talk, which I'm probably not going to be able to do very fast, I actually invented an early form of magnetic resonance imaging, and I published this paper, and I sent a copy to Paul Lauterbur. And Paul Lauterbur, actually, who is one of the people that really invented the very powerful pulsed NMR techniques for doing MRI read my paper. And so what I was doing was of course very similar technology, but not as elegant or as fast as what later came out. And so I think in a lot of cases, young researchers are challenged by nature to come up with new ways of probing nature, and these, you know, it's very important that these techniques be published, because in fact other people can then look at these and say, well, I can combine this with this other technique to make a vastly more powerful technology. So I think that, you know, one of the important reasons, motivations for continuing to do physical research, study nature, is in fact the fact that scientists are always being challenged to come up with new technologies in order to probe nature, and those technologies frequently have applications for mankind. So, very nice question. Thank you very much.
Bueno, pues si no hay más preguntas, pasamos a agradecer otra vez a Doc Osheroff el haber venido aquí. Muchas gracias.
And thank you all for coming. And I must say, I think I came a longer distance than you did, but there are a lot of you, and I hope you did learn something from my lecture. Thank you for coming.